12,800 years ago, Earth underwent one of the most abrupt climate reversals in the entire geological record. Forests across the Northern Hemisphere burned, megafaunal populations collapsed, and temperatures in Greenland fell by an estimated 5 to 8 degrees Celsius in a geological instant. This event is known as the Younger Dryas. It marked the sudden end of the planet's warming trend following the last ice age and plunged large regions of the Northern Hemisphere back into near-glacial conditions for more than a millennium. Today, scientists still debate the precise mechanism, but several lines of evidence allow us to reconstruct what happened with considerable confidence. To understand the Younger Dryas, we begin with the late Pleistocene. Between roughly 15,000 and 13,000 years ago, Earth was warming rapidly. Ice sheets across North America and Northern Europe were retreating. Sea levels were rising at rates far higher than modern averages, in some cases up to several meters per century. Vegetation zones shifted northward, and ecosystems began reorganizing themselves after tens of thousands of years of cold stability. Human societies were also changing. In the Levant, the Natufian culture began building semi-sedentary settlements and experimenting with the management of wild cereals. This is one of the earliest examples of pre-agricultural food intensification found in the archaeological record. In North America, Clovis period peoples hunted a range of fauna, including megafaunal species such as mammoths and mastodons, using highly standardized fluted projectile points. These cultural developments did not arise overnight, but were part of long-term adaptations to an increasingly productive post-glacial landscape. Then, approximately 12,900 years ago, the climate record shifts sharply. Greenland ice cores, particularly data from the GISP2 and GRIP drilling programs, show a dramatic drop in delta 18O values, a proxy for temperature, indicating rapid cooling. This shift is globally detectable, but is strongest in the North Atlantic region. The Younger Dryas lasted roughly 1,200 years before temperatures rose abruptly again at the onset of the Holocene, around 11,700 years ago. The changes associated with the Younger Dryas were not limited to temperature. Pollen records indicate a rapid return to tundra vegetation across northern Europe. In the Near East, drought conditions intensified. In North America, large mammals declined significantly, though the timing varies by species and region. Archaeological evidence shows that the Clovis cultural complex disappears from the record shortly after this boundary, replaced by more regionally distinct lithic traditions. These shifts suggest widespread environmental stress, but they do not, on their own, pinpoint the cause of the event. For decades, the leading hypothesis has been the meltwater theory. As the Laurentide ice sheet melted, it created massive glacial lakes, such as Lake Agassiz. Geological evidence, including beach ridges, drainage channels, and sediment cores, shows that these lakes periodically released large volumes of fresh water. One proposed scenario is that a major outburst flood routed large amounts of fresh water into the North Atlantic, disrupting the Atlantic meridional overturning circulation. Since this circulation transports warm water toward Europe, its weakening would produce rapid cooling. Climate models have reproduced this effect under realistic freshwater forcing, giving the hypothesis strong scientific grounding. However, questions remain about the precise timing and magnitude of the meltwater release. The meltwater disruption model remains the most widely supported explanation among climatologists, but not the only one under investigation. Some researchers have explored whether multiple moderate pulses, rather than one catastrophic event, might explain the complex regional patterns observed in climate proxies. Sediment cores from the North Atlantic and Gulf of Mexico record changes in salinity and ocean circulation around this time, supporting the idea that freshwater forcing played an important role. Yet not all records align perfectly with a single large outburst flood, leading to refinements of the original model and continued debate about how abrupt ocean circulation changes can be triggered. Another area of scientific inquiry focuses on internal climate system variability. Some studies propose that the Younger Dryas may represent a natural, though extreme, oscillation in the coupled ocean-atmosphere system driven by feedback loops between sea ice expansion, meltwater distribution, and shifting wind patterns. This type of mechanism is consistent with known climate instabilities during glacial periods, though the abruptness of the Younger Dryas remains unusually sharp even in this context. There is also evidence from Greenland ice cores suggesting changes in atmospheric dust concentrations, methane levels, and snowfall rates coinciding with the onset of the Younger Dryas. In the tropics, speleothem records from caves in China and South America document shifts in monsoon strength. These data indicate that the Younger Dryas was a globally significant climate reorganization, not merely a northern cold spot. However, the strongest impacts were concentrated around the North Atlantic, which fits best with an ocean circulation-driven mechanism. Turning to ecosystems, paleoecological studies show that vegetation zones across Europe retreated hundreds of kilometers southward within only a few centuries. Lake and peat bog pollen sequences reveal a return to cold-adapted plant species such as Dryas octopetala, which gives the period its name. Meanwhile, charcoal deposits increase in some regions, indicating that environmental stress may have altered fire regimes. In North America, large mammals declined unevenly across regions, with some extinctions clustering around the Younger Dryas onset and others occurring gradually over several thousand years. This pattern suggests that climate change played a significant role, though human hunting pressure on vulnerable species likely contributed in some cases. In the Near East, archaeological layers show that Natufian settlements became less stable as drought intensified. Grinding stones, storage facilities, and semi-permanent structures become less common. Some researchers suggest that the Younger Dryas temporarily reversed or slowed the trajectory toward full agricultural dependence. Yet other scholars argue that the environmental stresses of the Younger Dryas may have actually pushed communities toward cultivating cereals once conditions stabilized. In either interpretation, the Younger Dryas stands as a major pivot point in the development of agriculture, though the process remained gradual and regionally variable. For human societies in Europe, the return to colder conditions forced adaptations in subsistence strategies. Reindeer and other cold-adapted species expanded their ranges once more. Toolkits diversified regionally. In North America, post-Clovis cultures used a wider range of projectile point designs and targeted smaller game as megafaunal populations thinned. These changes reflect not a collapse of human populations, but a flexible response to shifting ecological realities. By the end of the Younger Dryas, around 11,700 years ago, temperatures began rising again with remarkable speed. Greenland ice core data show an increase of several degrees Celsius within only a few decades. This warming marks the beginning of the Holocene, the stable climatic period in which all of recorded human history has taken place. The mechanisms behind this rapid warming likely involved the gradual reactivation of the Atlantic meridional overturning circulation, combined with increases in Northern Hemisphere summer solar radiation, changes in sea ice extent, and shifts in atmospheric circulation patterns. As global temperatures rose, ecosystems reorganized once again. Forests expanded northward, and grasslands retreated. Sea levels continued to rise as ice sheets melted, eventually flooding coastal plains that once hosted Pleistocene ecosystems and human settlements. In the Near East, early Holocene conditions provided a more stable environmental foundation for the emergence of fully agricultural societies. Archaeological sites from this period show more permanent structures, domesticated plant remains, and increasingly complex social organization. In Europe, Mesolithic cultures adapted to warmer climates by diversifying their diets and exploiting a wider range of environments, from riverine systems to coastal zones. In North America, the post-Clovis archaeological record becomes increasingly regionalized, reflecting diverse environmental conditions as the continent transitioned from glacial to modern ecosystems. Although megafaunal extinctions left lasting ecological gaps, human populations continued expanding and developing new technologies suited to Holocene environments. The Younger Dryas remains significant not only for its abruptness, but also for what it reveals about the climate system. Ice core, sediment, and pollen records demonstrate that dramatic shifts in temperature and precipitation can occur much faster than once believed. Modern climate models incorporate these past events to improve understanding of how ocean circulation, atmospheric composition, and cryospheric changes interact on both short and long timescales. Although the conditions that triggered the Younger Dryas are not identical to today's human-driven climate changes, the event serves as a reminder that the climate system contains thresholds beyond which rapid transitions can occur. It is also important to recognize what the scientific evidence does not support. While researchers have explored a wide range of hypotheses, including more speculative ones, the data most strongly support mechanisms involving freshwater forcing, ocean circulation changes, and internal climate feedbacks. No single factor alone explains every aspect, but the combination of meltwater pulses, circulation instability, and feedback amplification aligns with multiple independent proxy records from around the world. This body of evidence makes the Younger Dryas one of the best-studied abrupt climate events in the geological record. For humans, the Younger Dryas demonstrates both vulnerability and resilience. Early societies were intimately tied to their environments, and climatic stress reshaped settlement patterns, subsistence practices, and cultural trajectories. Yet humans adapted, reorganized, and continued developing despite the challenges. As modern societies confront rapid environmental changes of a different kind, the Younger Dryas offers a scientifically grounded perspective. Climate can change suddenly, ecosystems can reorganize quickly, and human societies must remain flexible and adaptive in the face of shifting environmental conditions. The event remains one of Earth's most dramatic natural experiments, a reminder that even at times when human populations were small and technologies simple, abrupt climate shifts carried consequences felt across continents. Understanding the Younger Dryas is essential not only for reconstructing the past, but for improving our understanding of the climate system that shapes our future. Thank you for watching. Subscribe for more deep dives into the world's incredible histories.